I would like to invite our first presenter, Mr. Deb, from Mississippi State University. So we have one more minute.
I can note the
Yeah. Get yourself.
So good morning, everyone. I'm Deva, a graduate student attached to Department of Agriculture and Biological Engineering, Mississippi State University. Today, I'm going to present one part of my research on cotton SAM, AI-driven cotton ball localization for autonomous picking using YOLO and SAM integration. The United States is one of the largest cotton producers in the world market. The cotton production in the United States is concentrated in the cotton belt, which spans around 17 southern regions, including Mississippi State. The recent developments in AI and convolutional neural network have led to a widespread development and adoption of computer vision techniques in various fields. Additionally, robotics is playing a crucial role in revolutionizing this field with the integration of automation and computer vision. In agricultural context, specifically in cotton farming, computer vision presenting promising solutions to automate these cotton harvesting, specifically by detecting and harvesting cotton ball as soon as they open. So before we get into the research methods and the results, we need to get to know about the cotton harvesting and its challenges. Usually from bloom to mature, cotton balls require 40 to 60 days. So around 60 to 90 days, cotton balls start to appear. After 90 days, cotton balls start to crack open in preparation for harvesting along within a 1 month period. So this radical cotton harvesting uses a conventional, large and expensive cotton pickers. However, there's a heavy requirement to have a chemical defoliants that need to be applied before using these conventional cotton pickers to remove the leaves from the plant. Again, harvesting occurs when nearly all the cotton balls are cracked open. So these criteria presents a lot of challenges in the radical cotton harvesting. First of all, the radical cotton harvesters comes with high cost and their heavy weight impact the soil, plant root and penetration for water and nutrients, at the same time promising us sustainability issues. Additionally, the requirement of harmful and expensive chemical defoliants is required. The early open cotton balls will remain on the plant until the harvesting day, exposing to severe weather conditions over a one month period, thereby reducing the cotton yield quality and yield. So these factors not only threaten the sustainability of cotton farming, but also impose economic burdens while increasing the economic strain on cotton harvesting. So there's a heavy requirement to have a robotic cotton picker which can autonomously navigate into the field and could be able to pick the cotton balls at the right time, at the right place. So computer vision is one of the crucial components in this scope. So these are the two images that we developed the cotton farm in the virtual environment Gazebo and we tested. So in order to accommodate these perception or computer vision systems, we define two main objectives. The first objective is to accommodate computer vision to detect cotton balls in the farm environment. The second objective is to accommodate the localization of seed cotton fiber. So we want to apply segmentation to localize the seed cotton fiber for targeted cotton picking. So this is the cotton perception systems that we want to implement in the cotton picker. We call it as cotton eye. So this cotton eye consists of two subsystems. As you can see, the first one is the navigation assistance that will be implemented in order to guide the robotic picker throughout the cotton farm. The second one is the cotton ball localization system. That's why I'm going to discuss today here. So this contains two different cameras, left and right cameras. So first we want to do the cotton ball detection. Then we wanted to localize the cotton ball using segmentation. Then we use the manipulator to pick the cotton balls. So in order to develop these cotton ball localization systems, we began collecting images at a research field associated with the USDA in North Farm, Mississippi State University. So we utilized ClearPath Husky robotic platform, which contained 3 cameras, Z2i, OBD Pro, and RealSense V435 cameras to collect the images. So we collected a total of 10,000 plus images under various conditions along 12 days, such as cloudy, sunny, and partly sunny. So we labeled initially 1,008 images from the 10,000 image data set using RoboFlow for the model training. So our data set was divided into 3 sets. The first set is train set, which contains 740 images, which spans around 17.8%. The validation set contains 189 images, which accounts for 18.8%. And test set contains 105 images, which account for 10.4%. So once we have the data set ready, we train the model using a popular object detection model called You Only Look Once. So YOLO models were launched in 2016, and since there are a lot of variants available. So we utilized V8, V9, V10, V11 for the comparison analysis. On the right hand side of the slide, you can see two occasions where the YOLO can be utilized to detect the object of interest in agricultural context, and these 2 are from our lab research. So why these YOLO are popular, specifically in agricultural automation context? They are small in size, with quick computational speed, and they can inference objects in near real time, so that which is ideal for our application. So in order to check the performance of these models in a constrained environment, we define the hyperparameters as constant. So we utilize image size, initial learning rate factor, box loss gain, batch size, and epochs as constant for all these analyses. Once we get the best train weights for detection analysis, we wanted to utilize the segmentation process to localize the seed cotton fiber for precise picking. So in order to do that, we utilized segment anything model, which is an instant segmentation model launched in 2023 by Meta Research. This particular model was trained on 11 million images and 1.1 million segmentation masks. Additionally, this is a zero-shot segmentation model, that means it doesn't need an explicit training for that. So together with the YOLO, SAM can able to enhance the area of interest, that means in our case seed cotton fiber, to exact precise cotton harvesting. So this is the overall of current approach. We have the data set. So we trained using the YOLO. Once we get the best train weights, we applied some constraints, because when you are detecting the cotton balls, there are some cotton balls which are away from the first row, like second and third. So we want to restrict those cotton balls. So we applied constraints such as boundary box should be greater than one side of the boundary box should be greater than 100 pixels, and the confidence interval should be greater than 80%. Once we extract that particular boundary box coordinates, we apply SAM inferencing using segment anything model to extract the layers. So these are the overall results and validations for the YOLO models. So from the highlighted part, you can see that YOLO V9S achieved best performance with 0.848 mean average precision, 0.810 precision, and 0.779 F1 score. And YOLO V9E achieved best performance for recall with 0.759. And Gelanes model achieved best performance with F1 score of 0.779. Additionally, we also tested the train weights for our testing data set. So you can see YOLO V9S achieved best performance for mean average precision of 0.863, recall value of 0.776, and F1 score of 0.792. And additionally, Jelani model achieved best performance for precision with a value of 0.839. So during this multiple analysis, we found that YOLO V9S performed best for rating and validation and testing evaluation. At the same time, Jelani model performed well with testing evaluations for cotton ball detection. So we utilized these 2 models for further integration with the segment anything model. So these are the outputs that we utilized with the YOLO V9S and Jelani models together with the SAM model. Please note that we applied constraints such as one side of the boundary box should be greater than 100 pixels, and it should be greater than 80% of confidence level. So from this analysis, you can see, although these 2 models detected larger cotton balls, specifically Jelani model detected the medium-sized cotton balls where our manipulator can reach. When you see the performance of the segment anything model, it actually segments out the seed cotton fiber with high precision. So we have the data set with the Jelani model because we we choose Gelan E model for further integrations with the SAM, and we compared its performance with the other models. So FastSAM is publicly available model. It's the same zero-shot segmentation model, which utilizes two different types using FastSAM S and FastSAM X, which uses YOLO V8S and YOLO V8X. So we modified the code to display top 20 masks based on the confidence interval from highest to lowest, and we gave the prompt as cotton balls. As you can see from the previous slides, this particular detection failed to detect one of the larger cotton ball and one of the medium-sized cotton balls, and this occurred for whole data set. Additionally, within the top 20 segmentation masks, you can see some of the stems, dead leaves, and even some of the smaller cotton were segmented. So our cotton SAM approach outperforms the FastSAM based approach. We also noticed there are some failures specifically with the real SAM's camera because of the low resolutions. It failed to, the images were failed to detect and segment the seed cotton fiber. So A, B, C are the images. You can see where there is misinferences, specifically you can see from the yellow bounding box. And the image D, you can see a far cotton ball was detected where the most part of the cotton ball was covered by a stem. And the E image is the detection result using Gelan E model, using a real sense image, and the F image is the corresponding segmentation. So from these evaluations, we noticed that for the low resolution images, the SAM was not performing that very well. So future work revolve around fine-tuning the Gelan models, and we are also planning to adapt more, change the hyperparameters using genetic algorithms. And we can properly increase the resolution of the images, and we can maintain the accuracy and inference speed. We are currently expanding the data set, and we have currently around 1,400 images. We have planned to extend up to 5,000 images, and we will incorporate that in our further analysis. And we have the pipeline for SAM segmentation because we cannot analyze the performance of the segmented model. So we have already the pipeline for analyzing the segmentation performance of the SAM with the manual annotations, but we didn't start the work yet. We are planning to start soon so that we can compare the segmentation analysis of the SAM against the manual annotation, the area. So we are using the stereo cameras. So we are also planning to implement a depth filter using stereo cameras while applying this algorithm, so we can avoid the far cotton balls which are located beyond the first row. So in conclusion, we actually investigated YOLO V8, V9, V10, V11 for the cotton ball detection and segmentation for the robotic harvesting. Gelan E model performed well while detecting medium to larger cotton balls where our manipulator can able to reach with a high precision. And SAM model improved localization of cotton fiber for robotic picking and achieved relatively good segmentation results, but we are still cannot be able to evaluate its performance because we need to evaluate its performance with the manual annotations. So we are in progress of doing that. So I want to acknowledge Cotton Incorporated for funding this research, and Dr. Shin Jong and Sensing and Automation in AgriSystem Lab for providing good development and guiding through this research. And also want to acknowledge Department of Agriculture and Biological Engineering and MAFES for providing good environment and working opportunities to work with the cotton farm and my research. So these are references. Thank you.
Thank you for your nice presentation. We have a couple of minutes, so if you have any question.
YOLO V8 and V11 comes with segmentation capabilities, so why don't you use that
We wanted to, actually we didn't try that. Earlier model we tried using YOLO segmentation for the Gatsby-based simulation. So in the Gatsby-based simulations, we have a lower number of data sets, so the performance was poor. So we didn't actually try for this one. So maybe we can give a try in the future. Yeah.
Any other question? Yes, sir.
Great presentation, Deva. Actually, I have a few questions, but I can go for one or two.
Yeah, try one, pause.
So, one of the questions that I have is about segmentation, that you're just looking at the cotton plants over there, and there are a couple of rows over there, and the camera is right here. It's intelligent sense camera.
No, we are using 3 different cameras. For the field test, we use Z2i.
Z1.
Yeah.
So you're looking, and there are a couple of rows over here. So you see this row 1, row 2, row 3,
Yeah.
and cotton balls are there.
Yeah.
So all of those things are there. And then, based on my understanding, you are filtering out cotton balls to have, the cotton balls are the first row,
Yeah.
probably one side of the first row, based on bounding box dimensions
Yeah.
and contrast, you say?
Confidence intervals, confidence levels.
Confidence.
Yeah.
So sometimes what happens is that on the first row of cotton plants, there are some big or small cotton balls.
Yes.
Sometimes a part of the cotton ball is actually occluded with a leaf or something. And sometimes the orientation of the cotton ball is such that you see a little part of it.
Yeah.
So you have a cotton ball on this first row, which looks small and probably smaller than the other cotton, the second row of the cotton plant. You know what I mean?
Yeah.
So when you are filtering out based on bounding box size, probably you will get confused.
Yeah.
And if I'm not mistaken, maybe you have another level of filtering out based on distance from the camera, right? So do you think that's the best idea to go forward?
So currently, we already explored about that issue. So in the future, we are going to use 2 cameras. So in-hand camera as well with the arm, so it can move through the the canopies and it can able to pick the cotton ball. So that's a good question, in fact. So that can solve the issues. And we are using 6 degrees of freedom robotic arm. So you can work around different orientations. So like it's not going straight to the the cotton picking the seed cotton fiber. So 6 degrees of freedom means you can have multiple orientations you can reach even in the occluded scenarios as well. So currently we are not incorporated that study here, but maybe in the future we are expecting to do that.
I would like to hear this discussion, but I'm sorry that I am running out of time. Thank you so much for this. So our next presenter is Dr. Oi from UC Davis, and his presentation will focus on, I think you should get the entire. Thank you. And I'm sure this is it.
So hello everyone, my name is Ong Wei. I'm from UC Davis Department of Biological and Agriculture Engineering. I'm working at the Biology Lab. So the title of my today's presentation is called Active Vision for Enhanced Fruit Detection and Visibility with Gaussian Splitting. So some people may think all crops are harvested like mechanically nowadays, but in reality, pretty much all fresh market fruits and vegetables are still harvested by hand. So just give you an idea of what that means. So worldwide, we harvest about like 4.4 billion strawberries and 4.7 billion apples per year. Looking at these numbers need to be hand harvested. That's truly a big thing, right? And this is just the data for 2 types of crops. So fruit harvesting is extremely labor intensive, and the challenge here is that like the farm labor has been diminishing, and we can't find enough people to harvest. So what can be the solution to it? So one solution we think is to have the machines to do the picking, and another solution is to develop harvest aid robots to improve the efficiency. So our lab is exploring like both methods, but today we're focused on the robotic harvesting. So so although you may have seen some fruit harvesting robots somewhere, these machines are still prototypes and they are still under development. So why is it so difficult to build them? So the answer is actually it's not hard to build a robot that can harvest the fruit, but it is hard to build a cost-effective harvesting robot. Like one that is practical, that makes sense to deploy on the farm. So there are 2 major metrics, we think, that contribute to the cost of harvesting. So the first one is called fruit picking efficiency. You can think of it as the success rate of picking the crop from the tree to the bin. And the second one is the fruit picking speed or throughput. So to get a cost-effective harvesting robot, we definitely want to optimize both of them. but let's focus on picking efficiency today. So how is the efficiency calculated? So let's say the tree may have only have like a percentage of fruit visible to the camera, and from these visible fruits, only a percentage of them are detected. Among these detected fruits, some cannot be reached by the robotic arm because of some obstacles and due to some other limitations. And among these reachable fruits, like only a small amount of them can be detached, right? Because some may has already been damaged, some may fall on the ground, and some you cannot actually grab them, right? And finally, only another percentage of them can be conveyed to the beam. So clearly, the efficiency is the product of all these intermediate efficiencies. So how efficiently do robot and people pick reality? So the truth is that we don't have exact numbers on work efficiency, but based on our observations, we have done like people are about 90 to 95% efficient. They are pretty good at it. What about robot efficiencies? So from the publications we have read, people claim it ranges from like 40% to 90%, depending on the scale of the experiments. So we already see there's a gap here, right? So it's like, so yeah, if we focus on the detection in particular, we know that in most orchards, the fruits are occluded by the leaves, the branches, and also sometimes the other fruits. This significantly impacts the visibility and also the performance of our perception system. So people have studied the fact that if the visibility of the fruit is lower, then the confidence in detection goes down. So the higher the occlusion, the lower the confidence that the fruit is detected. So obviously, we definitely want high visibility and high detectability. So how do professional pickers harvest? Why do they pick so fast? So actually, they not only use, we think they not only use direct sensing, but also they create like mental models of the space inside their brains. So the model tells them what's in front of them in order to pick. Like how do they build these models? We think they build this by active viewing or active vision. This helps them to update their models quickly and also decide the next fruit to pick during harvesting. So actually, we observed that their sensing, their vision, and their actions are not coupled together. What does it mean? So for example, when they are picking one fruit, they are not always looking at it, right? They're actually looking around nearby to find the next fruit to pick, like they're doing this, like when they're picking another fruit. So we think this modeling and active vision strategies help them to discover more fruits and also pick more efficiently. I think we can mimic these behaviors in order to achieve the human-like efficiency. So to achieve that, we need to have first the sensing part of the robot, and second, the modeling, like how we build the representations of what's in front of us, and third, the sensor and the model-based actuation. So how can we build representation of the environment? Conventional approaches use voxels, they use point cloud, they use meshes. So these approaches are very common and well studied. But the problem with this method is that if you don't have enough viewpoints to build them, you will get the holes in the representation, and they cannot represent the space very well. Also, another problem is that they cannot be generalized or interpolate to give you the views of the world that you have not seen yet. So we want our representation to be able to create actually novel views from different angles, different directions, which can benefit the harvesting. So with the recent advances in the radiance field, scene representation, one promising solution we find is to use the NeRF, the neural radiance field, to represent the 3D environment. So you can take images of a scene and train a neural network to implicitly represent the space in terms of the geometric and optical characteristics. So here I show you some images like trained from nerve on different plants, and the result looks very good. However, one limitation is that since nerve is an implicit representation, we lack the flexibility to modify it as we want. Also, the rendering or the synthesis speed is relatively slow due to its array sampling strategy. So therefore, we choose another approach, which is called the 3D Gaussian splatting. So Gaussian splatting is another type of radiance field-based approach. Different from nerve, it uses an explicit encoding of the 3D scene with Gaussian primitives. So compared with nerve, its calculation can be computed in parallel and accelerated on GPUs. So make it very fast for both training and rendering. Another good property of Gaussian splatting is that it allows us to add a scene since the representation is explicit. So this short video shows a plan viewed from different angles that is trained from Gaussian splatting. We have tested Gaussian splatting on the real-world apple tree data set. So here, the first column shows you the ground truth images used for training, while the images in the middle are the rendered, the result from Gaussian splatting. So the results look very photorealistic and they match their input. And the last row visualized the Gaussian primitives in the shape of 3D ellipsoids used to represent the space. So the novel view synthesis results are also provided here on the slide. So as we can see, the generalization looks great. The synthesis can be run at 400 Hertz. That's very fast. And we believe this representation and high efficiency will benefit the vision-based planning, control, and also the learning in the robotic harvesting. I should have mentioned that this is an ongoing project, and I just started 2 months ago, so I only have some preliminary data to show you today. In addition, we have also created a very simple Apple orchard in simulation. So we use Helios, and Helios is a very powerful plant simulator that is developed by NASA Research Lab from UC Davis. And so within this simulator, we can configure how the plant grows, and also can create different scenarios. It also allows us to add cameras, and we can get images from these cameras. So the simulation also provides us the ground truth data for us to develop and validate our algorithms. So we applied the Gaussian splatting on the simulation data. Here's the original, then rendered images. I also show you the depth rendering from Gaussian splatting, and also the segmentation result if we incorporate some semantic information during the training. And more importantly, since Gaussian splatting is explicit representation, we are able to add it. So if you want to remove the leaves or skies, we can do that. If you only want to have the fruits, that also can be achieved. So here I show you some results that we use the grounded SAM2 to do the object detection and segmentations. Just to save time, I will go this fast. And we applied it on the simulation data. Also, we applied it on the real-world data with the prompt apple, and here with the prompt apple and wires, so it can detect all the objects very well and accurately. I'll skip these 2 slides. So how can we improve the visibility under the heavy occlusions? I think we can build an active viewing system. So this picture comes from a recent paper that published recently, where a robot arm is trying to select the best next view in order to discover more fruits and increase the visibility of specific fruit parts. So the results show that the active vision works and can definitely improve the visibility. So in addition, we also want to do the active vision without sacrificing the picking efficiency of the picking action. So we want active vision, but also not really using our picking arm that is picking to do the perception. So to achieve that, I think there are many possibilities that we can use other fixed cameras. We can using some arms dedicated for sensing only, or using some types of UAVs, carrying cameras, or even using some side cameras mounted on the picking arm to do that. And we will, to achieve the best viewpoint selection, we are developing algorithms that incorporate the feature information to quantify the uncertainty. So our active viewpoint algorithm will rely on this to compute the best next view. that maximize the information gain of the environment in order to reduce uncertainty. So like I said, it's an ongoing project and we have a lot of tasks to work on. So we are currently working on creating and updating the canopy models using the 3D Gaussian splats dynamically. In addition, we also have to close the loop by incorporating the canopy models in the robotic operations. So with the 3D representation, we can either apply conventional approaches such as the geometric primitives, like motion planning and control, for picking, or we can take advantage of some AI-based approaches to learn visual motor through picking policies using such as like imitation learning or reinforcement learning. I believe like we will have more results to show at that time. Yeah, that's the end of my presentation.
Thank you for your presentation. So we have a couple of minutes. If you have any question, please go ahead.
So when Robert was picking the any fruit, like he was collecting the damaged fruit, or like sometimes he will collect the damaged fruit, right? So only if you collect the good quality fruits. So that's my question. Like only if you collect the good quality fruits, or sometimes damaged fruits.
I think so. I'm not working. I think I'm working on the vision part, but I think maybe I'm wrong. But I think the damaged fruit is discarded. I think we don't collect this damaged fruit because you cannot sell it, right?
Sometimes if you collect the both fruit, it's too difficult for sorting to the next process.
Yeah.
So that's my question.
Go ahead.
Yeah, so two things. One of them is that you, in the efficiency that you showed through picking efficiency from the vision to picking transportation, one extra block I believe should be there, and that's damage rate should be added in. The second thing is that for picking cycle, we have actually multiple things. Camera takes an image and the image gets processed and localized, and the arm goes and picks it. So there's like, and then it goes there, picks it, now transports it. From here, that it goes to picks it and transports it, the camera is free and can take an image, then the arm can go for the next one. And when it takes an image, it takes an image of a scene, probably 10 foot away. So I'm just trying to understand what is the main reason behind this active vision method.
So I think two reasons. First one is I think so even if you have cameras taking images, right? Because from the pictures I showed you, right, in the orchard, it's heavily occluded. There's a heavy occlusion, right? If you take the images passively, some fruit will be missed, and you cannot be able to detect them.
So actually arm rotates and takes another image from here? Is that what you mean?
Yeah, so like from different viewpoints,
Got it.
like actively.
Got it. Thank you so much.
Okay, thank you. I'm sorry, it's 45 seconds already over. Can you please later on? Okay, thank you. Our next presenter is Chung-Hua Dong is here from Fort Valley State University. I don't know, in my updated list, I see only one presenter canceled. This is showing active presenter. So we can bring you back, Doctor. So we can continue this session. I don't know, they didn't cancel here.
Maybe I can answer a question.
Yeah. Yeah, this is the presentation, I believe. Yeah, Fort Valley State University. Is the presenter here? I don't think so. Okay, so you can continue the
The
question.
question is, you're using different technologies for 3D reconstruction, right? For example, Gaussian splatting. What's the plan for you to implement like in real time in the field? Is that possible, or what?
So the best result, yeah. So the result I show you, right? The images I show you, like we train within, I think 30 seconds.
Okay.
So we try to optimize it. We try to
The
reduce
inference time, 30 seconds.
no the training time.
The training
The training time, yes. So we try to accelerate the training by incorporating some new algorithms, and also reduce the memory usage because the Gaussian, since it's explicit, right, it takes a lot of memory. So we try to reduce that as well.
So when you inference, what's the inference speed?
It's about 200 hertz in average. It can reach like 400 hertz sometimes, depending on the resolution of the image as well.
So do you think it's possible to implement in like near real time in the field?
Yeah, that's our ultimate goal. We definitely want to achieve the good performance.
Yeah, we can continue another 10 minutes we had. So, yeah, it's unfortunate, yeah, because it's showing that only one presenter canceled, but this presenter is active, but I don't know. So, then I have a good question.
Yeah.
So, like, yeah, NERF, I read some papers, they used NERF for below ground, like 3D reconstruction of root system.
You mean NERF? You use
Yeah.
NERF.
So what is the difference? Nowadays people are using graphical neural network for 3D root reconstruction. So do you know about anything?
So the first one you mean NERF, right?
Yeah, NERF versus graphical neural network.
I'm not very familiar with the graphic neural network. Yeah.
Sure. Why don't you bring your presentation back? You are the presenter from Fort Valley?
I have one more question.
Okay, go ahead.
So I'm interested in the simulation part. So when you say, did you use the whole 3D Gaussian into the simulator or just some generated images to build a simulation?
You mean how we build a simulation?
Yes.
So we use the Helios. That's a plant simulator.
Okay.
You can grow like a tree. You can control the age of it. You can define the density of the leaves and branches and some other properties. You can also control the sunlight, the lighting conditions, the ground, the background.
So how, like, I maybe missed it. So how is it related to the Gaussian tracking?
Yeah, but actually we use the simulation environment to develop our algorithm, the pipeline. Like we don't have enough like real world data, right? And we cannot get the very accurate ground truth from these data sets. So that's why we start from the simulation, make sure it's working, and then we will move to the real world data sets.
Okay, thank you.
So what is there any time difference, like how much it takes for one plant or one crop?
You mean the
Time required to develop that?
develop in a simulation?
Yeah.
I actually customized the code, so it takes about like I think 3 minutes, 3 to 5 minutes.
Really? Go ahead.
So for all the images you use are just like a 2D image?
2D images.
Okay.
Yeah, I'm not using any depths images.
And yeah, so like then like you have this detection, right? You detect the fruit. You just train the YOLO model?
We explore different methods. We tested the YOLO. Also, we tested the grounding Dino plus SAM. I think they both give us good results, but definitely YOLO is much faster.
Okay. And the model is actually performing on the 2D images. So how do you render that to the 3D, like in the simulation?
So that's the good thing with Gaussian splatting, right? You can embed some mask, like semantic mask, to the pixels, and you can project it back from 2D to 3D through Gaussian splatting.
Yeah. Well, I'm also working on some similar projects on like the apple buds, and we're trying to achieve this kind of detection to the 3D. But right now we're using NERF.
Yeah.
Cool. We can talk more.
Sure.
You're using NERF.
Yeah.
One question about the simulator. So in the simulator, are there any 3D information, like the point cloud information included, or just the model, a tree, just like a tree?
So So the simulator itself can provide you point cloud, but we didn't use them. Also, we can get the ground truth Apple locations in space. So in the future, we want to compare the accuracy of our results with the ground truth.
So it's included in the simulation?
Yeah, you can get that information from the simulation.
Okay. Thank you.
Yeah, 5 more minutes. So if you don't, yeah, sure, go ahead.
It's not a question.
It's not for this, the previous one. We can bring the previous presenter. Is he here? Oh, he's there. Yeah, go ahead.
That's for
Yeah.
So when you work with this type of structured architecture of trees, right? I saw you work with, I'm not sure it's apple tree.
It is Apple.
Yeah, I came from Washington, and we have this type of planary, 2D shaped apple trees, right? It's not common, maybe not common for other crops. But how much, do you think if it's
Thank you.
very needed, if you have a very simplified, very structured tree architecture, for this type of active vision? I understand that if you have a really complicated, canopy structure, you probably need to find the occluded ones. But now, if you're working with a very simple, structured trees, 2D shaped, planary architecture, do you think the active vision is still needed?
It's a good question. I think definitely the active vision will work better for those like highly occluded scenarios. But for the simple structure scenarios, I think active vision will still improve the accuracy, but like by a very small amount. Yeah, I don't know how to answer this, but
Yeah, that's okay.
yeah.
Thank you.
Anyone want to ask? Okay, go ahead, sir.
So when you're creating a simulation and an environmental simulation, there can be some difference compared to a simulation in real time. So for example, the sky can be different, the plants will be moving due to the wind. So is there anything in simulation that we can change to make those effects so that the transition from simulation to real time can be more smooth?
So in the simulator we used in Helios, you can control the lights. You can bend it very fully realistic, but you cannot incorporate the wind. And currently we are only considering like stationary or static scenarios. That's maybe one of the limitations of this method. But I've read some papers that people are developing advanced Gaussian splitting for these dynamic things. So I think we can incorporate those methods to solve that.
How many images you use to develop one plant structure?
So for the result I show you, I used the 10 images. Yeah, 10 images to get that result.
Those the result from 10 images for one.
Yeah, 10 images trained within 30 seconds.
Really?
What kind of GPU?
I'm using the 4090.
4090? Yeah, because we
I
are.
cannot get 59.
Yeah, we are also trying, but we develop a computer vision system so that we can take we are rotating con root 360-degree rotation. So every 1 degree rotation, we are collecting image. Then we have, for one root, we have 360 images for top, front, and side. Top and side. So we have 720 images for one root. And for us, even 4090, it takes more than 5 or 6 hours, I believe. So, yeah, but your image is a color image or monochrome?
Color image.
Color image. Yeah, this is very less time. 3 minutes, yeah? I'm surprised. Okay.
Yeah, very good.
Yeah. If not, I think we can take this 2 minutes for coffee. If someone needs coffee, you can go for coffee. And please bring bag. And give you some heads up, like 11 a.m. presentation also cancelled. So if you guys want, I just noticed last night in the online agenda they replaced that presentation with my name, and they want to show something. So I will show you 2 slides, and I want to use that 15-minute presentation as for brainstorming session. I want to learn from you guys, okay? So if you all agree, then we can utilize that 15 minutes. If not, then you are feel free to take coffee and look around, okay? Okay, so our next presenter is Mr. Rafi from Auburn University. Oh, you're here. Great. So please prepare. Great, thank you, Dr. Wei. I'll ask the organizer if we can provide some special award to you for answering all these questions.
Let me know how to start.
Yeah, sure. And I will show you this, okay? When you continue 10 minutes. Go ahead.
Hello everyone, this is Mutasim. Oh, I'm sorry. Hello everyone, this is Mutasim Hadi Rafi, and I'm a master's student at Auburn University, and my work is on ornamental plant nursery management. And for this session, I'll be presenting a portion of my work, which is cloud-enabled plant segmentation and tracking framework for the ornamental nursery, obviously. And before I start, can anyone give me a quick head count how many people are there in this room? Well, that might take a while, but I'll tell you, this will take a while.
Yes.
Now, imagine doing this in the ornamental nursery. The nurseries are spread across usually thousands of acres. The plants are spread across the bed like this, and it's entirely manual, and there's no scalable solution until now. And the industry is 160 billion big. And so it's error prone, we are doing hard work, labor, and the labor cost is increasing day by day. So what is the viable solution that we can provide here? Of course, it's deep learning, right? Now there are models like YOLO and SAM, segment anything, only locons for detection and segmenting, all those things. But when you're deploying them in the large scale, you have to either go with a panoramic image or a video. Now, if you go for them, what happens? You want to count them, so you will get repetitive counting because you stack images to make a video, right? So one plant may appear in the multiple ones. So for that, you either have to stitch the images to make a panorama, or you can track the unique objects throughout the video. So what's the issue with the image stitching? Like if you want to make a panorama, it will suffer from ghosting effects and white baselines, distortions, and stuff like that. And it really needs high computational power. So the other viable solution is tracking unique objects. Now there can be 2 kinds of tracking. One is visual tracking that is provided by segmenting model, and another version of that is Samurai. But for that, you have to prompt for every unique object. Now if you can prompt for every unique object, you already have the count, right? So this is not suitable for counting. So the other option is multi-object tracking algorithm, or MOT. Now there are different kinds of MOTs, but all of them suffer from missing boundary objects. They suffer from identity switches, like if one plant is coming throughout 30 frames, maybe it's identified as plant 2 in 10 of them and plant 5 in the rest ones. So you will miscount over there. And there are misclassifications due to the model. So what I propose here is we want to build a nursery bot, or a rover, that will go across the field, collect the data, and we'll have developed a multi-object tracking algorithm named KV-Track. It will track the unique plants for accurate counting. Then the backbone of the plant tracker will be an ensemble model. The model for the backbone, and we want to put everything on a cloud architecture system so that you can get an entire dashboard and see what's going on in your field. So before I go to the data collection pipeline, we have this rover. It's from FarmNG, and we equipped it with NVIDIA Jetson AGX 64GB, one OcuPro camera, and one Richard GS, RS2 GPS. And this is the field of view from the camera. And apart from that, we have also used DJI Mavic 3M UAV, and it's to map the nursery. And this is a portion of the map. Now, regarding my data, we collected data in 2 seasons. The first one was in August last year, and this is small data, and there was another data that we used for test, and it's a large set of data. Usually what happens, you train on a larger data and test on the smaller data, but we want to do the opposite because we want to test it on diverse conditions. So this is my training data. It has no variation. We collected data from 2 plants, Azalea and Sunshine, and for the test data, we took data in different lighting conditions, we took data from different growth stages, we took data from different variation of the same plant so that we can test our algorithm because we are assembling 2 models. And this is the ensemble model where we have used 2 models. One is cut-mixed based model and another is transfer learning based model. Then we use the softness classifier to combine one single result. Then we gave it to the tracker, and the tracker gave us the counting and other information. And before I go to the conventional our tracker, I want to talk about the conventional multi-object tracking algorithms. What happens there? They track throughout the current frame of a video and the previous frame of that video. So this is what we call the short-term association, and they use Kalman filter to collect data from to get the motion of the unique plants or unique objects throughout the frames. So this is what causes the identity switches and other misclassification issues. And this is the example of byte track. So what we did is we added another layer on top of byte track, and we named it kilobyte track because for this we are taking into account for multiple frames. So if one frame has, let's say, 5 objects, then we take the older object and see how many frames it appeared through, and we stack those many frames and divide the frames into 3 portions. So one portion will have, for each unique plant, it will have how many appearances they had, how many, what's the area of the plant, like if 2 plants are occluded together and with different field of view, you can see that it might be different object in some other FOV. So we compare all that. Maybe one image was, plant was classified as Azalea in some and then Sunshine in others. So we also take into account and we combine all of them together to get the proper count. And finally, we have put everything on a dashboard. So this is the dashboard, this is the map. You click on each bed, you get this dashboard. There are morphological data as well from the segmentation model. And on top of that, you can also download an Excel file to get the report, entire report. And we have compared our algorithm since it's the result of the comparison. We have detected and segmented. We don't put the boundary boxes, but it was detected first, then it was segmented. And we have compared our result with YOLO specifically because YOLO is the only model which is capable of both detection and segmentation. And in terms of MAP and other parameters as well, we stand out both in detection performance and in mask performance or segmentation performance. And this is the final result of MOT. I will do a comparison. We compared KV-Track with DeepSort, BotSort, and ByteTrack, 3 other MOT algorithms. For the first one, if you look at this one, this is the same plant in 2 different frames of a video, and one plant was identified as 276, which became 289 in the other. Same happened in BotSort, 329 became 356. And finally, in ByteTrack, one track due to the occlusion was identified as 401 and 441, which later became only 441. So in KV-Track, we have solved this issue and it's not there anymore. So for counting purpose, because we count only the unique IDs, so for counting purpose, KV-Track stands out. And we have put KV-Track with different backbones, not just our ensemble model. So there are different versions also of YOLO. And we stand out in terms of MOTA or multi-object tracking accuracy, MOTP or multi-object tracking precision, and identity switches. What is identity switch? When a object is maybe it was ID2 in some frames and then it changed its ID to ID7 in other frames, that is identity switch. So we want least amount of identity switches. So we stand out in identity switches as well. However, for higher order tracking association and frag, we lose this because this is a layer on top of other multi-object tracking algorithm. So we are reassociating the IDs with this. So in higher order tracking association and in terms of fragmentation, we lose our capability, but for counting, this is the perfect scenario. I'll tell you this. And we have compared our result with different algorithms with different backbones, and the best result comes out with our ensemble model and our KB track. But in this case as well, you will see in all the backbones we stand out in case of MOTA, MOTP, and identity switches, not the fragmentation and HOTA. And this is the performance of our counting. If you look at over here, our predicted count is way better than that of predicted count of deep sort, bot sort, and byte track. And our RMSE value is it's below 1. And in conclusion, we have developed a multi-object tracking algorithm with long-term association, unlike the conventional ones. Then we developed an ensemble model as the backbone of this, and finally we have put everything on the cloud architecture system. And as part of my future work, we want to optimize this for real-time deployment. And also, since the camera we are using is an OGD camera, it has the stereo capability, so we can create point cloud or other 3D imagery system from it. So we want to do that for a better morphological analysis. And I want to acknowledge my lab, Precision Agriculture Lab, my Department of Biosystems Engineering, and USDA and NIFA for funding this project. And these are my references. And thank you very much. I am ready for questions if you have one.
Thank you.
Yeah.
Could this also be used for other types of inventory, for example, for livestock management?
Yes, it can be used for that.
So, for precision animal management.
I'll tell you this. The algorithm is specifically for counting. The model is for plant. So if you train the model for livestock, it will work with the MOT algorithm as well. So, yes.
Like for precision livestock management, if I understand correctly your question, occlusion is one of the main issues,
Yes.
right?
Yes.
So you cannot control the chicks.
Yes.
So I don't know how we can.
So what happens? The MOT algorithm doesn't care what detection process it's getting. So it only detects based on the ID. It doesn't know if it's a plant or if it's a livestock. So if you train a model for the livestock and then put the MOT algorithm on top of it, yes, why not? It will work.
Yeah, so we basically still have 3 minutes, so we can ask more questions. Yes, go ahead.
So, if you look at deep sort or those tracking algorithms which use image information and keep the initialization image and try to track the object over time using image features as well, how effective do you think your algorithm is?
Well, my algorithm doesn't really work a standalone application. It's a layer that you put on the top of other MOT algorithms. So in our case, I put the KB track on top of byte track. So what happens here, it gets the detection and the tracking from other tracker, then it analyzes over multiple images, unlike the previous one.
Okay.
So
It's like post-processing after
yes, yes.
appending.
Any more question? Go ahead.
Amazing presentation. So I'm kind of confused. You compare different backbone. Because I remember you put YOLO stack there, right? So I wonder if the tracking is based on segmentation or is based on detection. Because yeah.
Oh, okay. The YOLO model has the capability to detect and segment together. the YOLO V11. So our ensemble model works on top of that. So it was trained from YOLO. So it can work on both segmentation masks or the detection box. So in our case, we have used the segmentation one because the plants often come out occluded together. So if you have the segmentation mask, then it will perform better.
Okay, and then you mentioned you only use part of like very little data to train. And I wonder how does that work for segmentation? Because normally it takes a little bit more images to train.
Actually, so here is our data set, but even in here, if you look at the train data, it's not that small. It was 227 images for Azalea and 178 images for Sunshine, and in total they had more than 1,000 plants in each in together. So when I'm saying that test data is small, it's smaller than the training data, but not actually that small.
And you are fine-tuning or training from scratch?
I am fine-tuning with some augmentation. Like I'm ensembling two models. One is the cut mix based model. So what happens in cut mix, you cut a portion from one image, then put it on top of other image. This is one kind of augmentation, and for the other, we are doing a feature intuitment with transfer learning. So both are trained from YOLO V11 models, but with different augmentations, so that we can work on the diverse conditions. I'm sorry. So that we can work on the diverse condition.
Yeah, we can continue because next presenter is cancelled. So go ahead. We can toast him.
I'm fine with that.
Sure.
So I'm curious because I'm interested in this. So when we talk about occlusion, there are different types of occlusion. In your case, since you're working with plants, your objects don't move. And the occlusion happens when one plant is maybe overlapping with other, but they're not really moving. It's a camera based.
Yes.
In general, I work with livestock, so we put a stationary camera and the animals move everywhere.
Yes.
And sometimes they just overlap with each other and doesn't move for long periods of time for minutes. So, do you suggest or do you think your solution can deal with that, or do you
Well, what I believe is if you can do it visually by yourself as a human, you can do it with AI. So if that occlusion, if from one stationary angle one man can't detect, the AI can. But if one man can detect, yes, of course, you can do some, like if this can work, you can obviously do some fine tuning and make it work, yes.
So this research is only focused on counting, am I right?
It's actually the multi-object tracking algorithm that we specifically fine-tune for counting, but you can use it for surveillance or other applications as well. In our case, it was counting.
So can you use like to collect after this, can we implement your algorithm further fine-tuning like for phenotyping parameters or any other?
Yeah, we can do that actually. Yes, and that is also part of our project on a different perspective. So another lab mate is working and he's actually presenting on some other room.
These images acquired using UV or?
No, they are from ground to
UGV, like top
UGV,
camera,
yes.
okay.
For the actual phenotyping, if you know that, you probably need to use the stereo camera.
Yes, that is, right now I'm actually working on this. I recently started working on the point clouds also with stereo cameras.
Okay. If there is no more questions, so we, go ahead, sir, yeah.
Just go back to the first slide first.
Yeah, we have time, so please.
Thank you.
This one?
One on go. Keep going.
This?
There. Thank you.
Sure.
Thank you.
Okay, so please. Yeah, so now do you want a break or you want to continue? So we have 10 more minutes left. Break? I would defer you guys. Or I think or if you want, I want to show you a couple of slides that I experienced from one of the farmer in Tennessee. So, yeah, I'm from Tennessee. So, let me start that, okay? So, yeah, that farmer, actually, he's very technology friendly guy. If you go his farm, he has autonomous tractor, even Germany's tractor, okay? So he's very technology friendly, right? And he has his own drone for broadcasting spraying. So he recently actually reached out to our department and he wanted to work with us. So his target is during earliest stage of, he wants to detect earliest stage wheat, okay? During, especially his focus is germination and vegetation stages of corn growth, because that stage actually, if you can control the wheat, you can say increase your yield significantly, okay? So, and his target is to identify both of them. So he wants to identify narrow leaf as well as broad leaf wheat, okay? So, and his final goal on this, the last one, site specific spraying drone, okay? He wants, his ultimate goal is that. So now, when we discussed with him, and one of my graduate students from Thailand, we spoke with him together, and we said, okay, you want low cost, time cost effective, and as well as time efficient, okay, with detection method, his target. So we told him, okay, can you do this? Like, in terms of hardware, we can reduce the camera cost. We can buy low cost camera, less than regular RGB. Operation flight, if we can use low resolution aerial imagery, that will be one parameter to reduce the cost. And also we can reduce the processing time using object-based image analysis and machine learning application, okay? Those are technical things. So then he allowed us to fly drone on his field, okay? So what we did, on the same field, we choose 1 hectare area of the field, and we flew like 50 feet high, 100 feet, 150, 300, 375. Okay, these are the images. And my student, she summarized and she said, at a flight height, to acquire aerial images at a flight height of 50 feet, sorry, it's meters. It should be 15 meters in the parentheses. 50 feet over a 1 hectare corn field consumes 3 to 6 times more flight time compared to 100 feet and 150 feet respectively, okay? So that means 50 feet high, we will get more good quality image, am I right? Maybe we don't need more sophisticated image processing technique compared to 100 feet. So, but on the other hand, the disadvantage of 50 feet flight height, you have to change battery frequently, okay? That the farmer doesn't want to do. So he preferred to take coffee for that time instead of changing the battery, okay? This is what the conversation with him. So now, my question to you guys, so I am not an expert for UV image, so you guys are expert. I believe you guys are expert. So could you please answer, can we discuss this question? What is the recommended flight height that would reduce flight time and minimize battery changes? Remember, our target, ultimate goal, accurate wheat detection in a cost-effective and time-efficient manner, okay? Because Tennessee farmer, you cannot consider them as California farmer, okay? California farmer can afford $50,000 or $20,000 drone, but Tennessee farmer, they will think twice, okay, before they purchase any technology. So, I want to discuss this for this, I don't know how many time we left. Of 8 more minutes. So what can we do? Do you have any suggestions? Do you want to share your experience? Yes, sir.
So I was working on a project for detecting field crops in US using satellite images.
Yes.
So I was dealing with a 10-meter resolution.
Yeah.
So, but our task was pretty simple compared to this. We just need to find where the wheat fields are. And we did some experiments in Kansas. We took some counties, and our modeling approach was also considering the resolution. So since we have a 10-meter resolution, we just take a small grid of 3 by 3 pixels and assign whether it's a wheat field or not in those 3 by 3 pixels. So we had challenges of like getting good satellite images due to weather conditions, all of these things. So, but I think if those kind of techniques can be applied, it can be done with lower resolution as well, without looking at object detection methods. If you're looking at like segmentation methods, like you have a big image and you are doing processing.
I connected with the WebEx, so I don't know. Because someone joined virtually, so I think I should just show. Okay.
Yeah, so if we do a kernel-wise crossing, like we do a sliding window kind of crossing, and try to predict in that kernel is there a weed or not. Maybe if you change the algorithm that way, you can get away with lower resolution and higher amplitude crossing.
Okay. Thank you for sharing your experience. So any other?
So the drone is just taking the images, not
Yes.
actually spraying.
Yeah, not actually spraying. It's just for weed detection, okay? Then later, because you cannot fly at the same height, if you detect the weed, at the same height you cannot spray, am I right? So you have to adjust the height. So that is later, but first, actually, I would like to suggest him at what height is suitable for him. So he reach out. If I fly 50 feet, even 30 feet, so he has to change battery 3 times for covering 1 hectare field. So he reached out to us. He wants solution as an agriculture engineer. So and then we went his field. We flew at different height, and we noticed that at 150 feet we just need to change 1 time the battery. Yeah, of course it's a low-cost drone. It's not a fancy drone, DJI Mavic 3. Okay, so but he wants that solution. So okay, tell me at what height I should fly drone. So that I don't need to change the battery frequently, okay?
I think this is a very good research question.
Very good.
Because like you also listed like the
Yeah,
weather
this is
conditions.
just last night I prepared this final slide. So can we discuss on this topic? Which parameter should we consider? Resolution versus efficiency, battery life, field size and coverage, or camera specifications? Of course, Tennessee farmer that say they are poor, they are not rich farmer. They are looking for low-cost sensor.
I think an important point you have there is weed size. I don't know if we have any weed scientists in our audience, but sometimes they are very concerned about very small weeds, right?
Yes, sir.
So that is part of the challenge.
Yeah, you see, he want to detect both of them. So he want to detect this plus this.
Yeah.
Because he said, for this I have to, my herbicide rate will be different compared to this one. So, yeah, I think we have 2 more minutes. We can talk. If anybody has any other advice. Do you have, sir? I think you work with drone a lot of.
I think companies are trying to come up with high resolution images.
Yes.
That's the solution. There are 40 megapixel cameras and high resolution cameras. There are military-based cameras being used, but they're expensive for farmers. Increasing the camera resolution would be the solution here, but we don't want to increase the cost of UAV. I think we are limited with technology here, rather
Yes, sir.
than how can we improve it is a very good question. number
Yes.
of pixels that represent the target is important.
True. Yeah.
So I have one question. So in this regard, like we are taking drone image
Yes.
with the, let's say, the area coverage of 10 meters or like 1 kilometers. How much?
This is-
resolution we have,
Uh,
and then we would have the very like high resolution image. So I have one question. My question here is that how we could, in an efficient way, correlate one image of 1 meter square with high resolution. Each pixel with the 10 meters or 1 kilometers of the image, satellite image or drone image of 10 meters. So how we would do, we can do more efficient correlation of those pixels with that pixel.
Yeah, that's a very good point. Actually, we are thinking that way, I don't know, I have this. I should have that. Yeah, this is we are thinking that at different pixel size, resolution like this. So 1 centimeter per pixel, 3 centimeter per pixel, 5 centimeter per pixel, 10 centimeter. Are you talking about this?
Yes, but here 1 centimeter pixel size of that we get it from a high resolution camera, and comparing of one pixel with the let's say 100 pixel of the drone image. That would be how you would correlate this in a more efficient way.
Would you mind, we can discuss later,
Yes,
okay? I would like to back to the studio. So our next presenter is Dennis Olgan from University of Georgia. Please go ahead, sir. Yeah. Sorry, okay? Thank you.
Good morning, everybody. My name is Dennis Olgan Kiopia. I'm a PhD student from University of Georgia under Dr. Glenn Wines. I'm going to present to you about automated deep learning techniques for classifying whitefly population on cotton leaves. This is a kind of ongoing project, but the main idea is to design a kind of robotic arm or a kind of handheld device which can detect whiteflies in the multiple leaves. So I'm just going to talk a little bit on what we see in multiple leaves compared to other people that have been observing when they detect those whiteflies on one leaf. So for those who may not know these whiteflies, okay, these are the whiteflies. They are very small, like 1 millimeter. So when you talk of detecting them, is a kind of an issue because they are very small, and we are trying to use very small, inexpensive cameras like Raspberry Pi cameras. But again, even though they are small, like 1 millimeter, we are also trying to see if we can classify them based on being adult and being young. So we'll be talking about the adult ones, which are the adult ones on the left video, and the small ones, or the young ones, which are the NIF ones. Actually, these are the major pests. They go over different crops. We are working in cotton, but they also go to vegetables. So they're very bad because they do not only damage the crop, but also they lead to virus in the crop. Currently, traditional what people are doing is to go in the field to check the number of these whiteflies. If about 40, if the images in the canopy have 3 whiteflies, then you should go to apply pesticides. But if one of the leaf has got 5, then it's dangerous. Apply pesticide. If maybe there are 5 young ones, then it is also dangerous, upright exercise, you see. But the major challenge is they are quite different from other pests. The other pests stay on the top of the leaves, so you can pass with camera and you can see them very easily. But these ones, they stay under the canopy, so they are hiding. So we are trying to see if we can develop something that can actually go under the canopy and see them and do some kind of counting and then do some prediction on the all over the canopy, and then from there give a kind of decision. So, as I said before, what other people are doing, this is not the first kind of work, but most of the people have been like taking one leaf in the greenhouse and try to locate the whiteflies and go for deep learning, and they come up with like a good decision accuracy, 90%, 99% detection of these. But if you look on one leaf, maybe easy because you are just working on one leaf. And if you are working on greenhouse, the environment is different from working in the field environment. So for us, we are first trying to see in the field environment to do a kind of localization to understand the behavior. If you have a big canopy, where should you focus your sensors? Should you focus the sensors on the top of the canopy, in the middle, or on the bottom? So the other thing, we are trying to use this kind of YOLO to see if we use this light model detection models, is it possible to see at least some number of whiteflies based on the two classifications, the young ones and the adult ones, and then based on multiple leaves, and then also considering the field conditions. So a bit what we did, this is the field. You can see the field on that picture. You see we have some plants which we are monitoring, and this you can see some flags. Those kind of plants we are monitoring daily, and we compared a total number of whiteflies in the whole canopy and the total number of whiteflies in some nodes in the plants, so that we understand the section of the canopy where we can get those whiteflies in case we wanted to use some robotic arms, which we haven't done yet. Basically on the behavior, what we observed so far, these whiteflies, they stay on the top canopy, top part of the canopy. So this is good information for us to start thinking, if you want to design a system which can go over the multiple leaves, then we should focus on a certain area of the canopy rather than focusing all over the canopy. And we have found that if you focus on such kind of top nodes in the plant canopy, you can observe about like 44% of the entire canopy for what we have done for now. So the second step is deep learning. So we collected about 1,000 images, and then we did a kind of training, and then based on 80% training and 20% validation, and we have done a kind of comparison to the precision, recall, and F1 score, but just based on two classes, the adult and young ones, and we are trying to see which one, these models, where do they perform very well, on the adult one, on the young ones, and what is the percent of detection. So we observed the behavior of our model during the training. Actually, we could see like the errors are dropping during the training, but we observed during validation, we have a lot of dynamics in terms of errors. We think possibly it's because the images were raw. We didn't do any processing, like cleaning the background, because there are like soil background. There are other leaves which are like dry, they look like leaves, they look like young ones. We didn't do anything. This is like really natural environment. But in terms of recall and precisions, yeah, we see some increase on the training, like we can do detection. Yes, in terms of the results, we compared YOLO V4 and YOLO V8 Nano. We see like YOLO V4 could not do very well on the same images, same image size. You see like adult ones, we could get like 44% in terms of average precision. But if you go to young ones, the multiple leaves, you just get like 19% when you are using YOLO V4. But if you go to like Euro V8, you start getting like a little bit good, reasonable detection, because we get like 70% on the adult ones, but also you get like 44% on the nymph, which is a bit improvement compared to Euro V4. In terms of mean average precision at 50 threshold, we see like still Euro V4 is not doing very good, but Euro V8 is doing a little bit of good improvement. And if you go to recall, we see like Euro V4 could not recall very well, like only 50%. But if you go to Euro V8, you get like a little reasonable recall. In terms of F1 score, we get also 64% on Euro V8. So that gives an indication that we can continue keeping on, we can keep on this kind of project to see if we can design a kind of a device which can detect this small pest in multiple leaves. So we compared this also like a kind of small testing and visualization. We see like when we use Euro V4 on the same image and Euro V8, we see like on the same image, this you get like 31 whiteflies being counted, but if you go to Euro V8, you get 67. So it's kind of an improvement. So like on the same image, you can get different number based on which model you are using. If we think of an image which is including both classes, adult one and young ones, we see the Euro V8 is also still doing better on the young ones, because these are the ones which actually looks like very difficult to detect in multiple leaves. And we think the major reason is we are still analyzing these images, but one of the things we think is this, even though they're small size, but the models are currently being under-trained on the nymph because there are very few nymph in the data set. But the other thing is because these were taken all over the season, they have different variations, so the model are kind of trying to struggle to see how to detect them. So maybe we needed to add more data sets, or we need to do more kind of cleaning, but also because we are using boxes to do the detection, maybe segmentation may be very good. The future work, we are trying to develop a kind of platform for real-time detection for farmers. Maybe that may be attached to a robot, or maybe a kind of handheld. But the other thing is to do a kind of map-infested localization, to develop a whitefly heat map. But the other thing is to improve the spatial and the temporal spray management. That will be the other work. We tested our model on the other, we know this one, people do detect these, monitor these whiteflies using sticker traps. We tested our model Euro V8. We can see it managed to count like 100 whiteflies on these images, and like 300, something that we cannot do by our eyes. But what does it mean? Here, this kind of technology is used to monitor the adult ones which can fly toward that sticker trap. But our model could not see the nymph on these ones, detected only the adult ones which comes to this one. So it looks like our model is doing well. So in conclusion, whitefly can be observed more on the top section, which is good for us to design devices which can work on the top section of the canopy. And Euro V8 can perform very well compared to small versions. And then sensors can focus on detecting and leaf whiteflies without scouting the entire canopy. So this is the team lab work. And some of the professors who are advising us. We thank the University of Georgia and USAID, and we thank you for listening.
Thank you for that presentation. So, if you have any questions, we have 3 minutes left, so please go ahead.
So I have one question. Like you mentioned about one pathogen, maybe the whiteflies. Is it applicable for other pathogens like aphids? Because aphids is also very damage in cotton. So is it applicable for the aphids also, like other type of pathogen?
That's a good question. It can work, but we haven't trained for aphids. We just trained for only whiteflies. But I think it's a good advice that we may include into our model because they all go together. Somewhere where you find these aphids, you may also find whiteflies. Yeah.
Are there any challenges for end users, for farmers, or producers, if this product came to life? What challenges do you think this results producers, or how do you think about overcoming those challenges?
Oh yes, there is a big challenges because some people what are doing currently is if some farmers they go for consultants to hire them and go to the field to scout manually, to count and come up with a spreadsheet, like now apply pesticides or do not apply pesticides, just wait. There's like a low population for now, or they are not there yet. But some farmers, what they do, they go on to another challenges because they just apply regularly. Like, okay, I know it's over the season, I have to apply like twice or 3 times in a season. So it means they use a lot of pesticides unnecessary sometimes. But if they are there, that's good. Yeah.
So whiteflies are very tiny, and is it necessary we actually know the exact count, the number of the whiteflies? Can you just, because the yellow sticky card, we have the fixed size, you install the trap, and each time you can segment the pixel, for example, from the whitefly, and compare it to the yellow sticky card. Can you think that's a...
Yeah, that's a good contribution. So far, what we are trying to see is to understand the population in the leaves, and also to understand the population that is moving toward the stick top. And then from there to see whether these two can correlate together to give the decision. But not only that, on the stick tape, we get all the adult ones. But if you go to the leaves, then you can monitor the young ones. And the young ones are the ones which are very bad, because once they're hatched, they can stay over there and damage the entire leaf. Yeah.
Okay, go ahead, sir. You have 1 minute.
So since the objects that you're trying to detect are really small, and the way YOLO or other object detection models are designed, it's hard for them to detect really small objects or really large objects. So have you considered trying dividing the image into like some quadrants and then train a YOLO model? Since you have the annotations, you can probably like divide the image and divide the annotation size accordingly, and have you considered trying that so that it may improve the model detection performance?
Yes, that's a good observation. I think we'll try doing that. As I said, this is kind of observations and a raw image. We are trying now to do another processing techniques. We see like the one we have proposed, some people have done that when observing the whiteflies on a single leaf, but we try to see if we can also do the same on multiple leaves.
Okay, thank you. I would like to stop here. So our next presenter, Ms. Young. Young. Okay, sorry for my mispronunciation. She's from Pennsylvania State University.
Or you can call me Dr. Yang.
Dr. Yang.
Hello everyone. So I'm Yan-Chu Yang. I actually just defended my PhD like in 1 month ago.
Congratulations.
Thank you. So today I'm going to talk about the last project that I actually did during my PhD. In early 2024, Penn State Extension reached out to us, asked me to develop this tool if we can use AI to control this invasive box tree moth. So this moth has potential to spread to Pennsylvania at that time. Well, quick check. Have you ever, when you travel abroad, the flight attendants always ask you, did you bring any plants or animals, right? So the pictures I actually took in Hawaii. When I go there at the airport, there are signs everywhere that the USDA trying to tell us to protect American agriculture. Do not bring any plants back to the mainland US. Well, invasive species is a very big problem, but we as humans are the ones to be blamed. And it can cause harm to the environment, even human health. This is the infamous spotted lanternfly you may know of. So since it's first found in 2014 in Pennsylvania, now just 10 years, it's spreading to 18 states. Every time when I present this, I have to check and update this number. Well, it has spread it, including New York State. And seems like New York State is taking its revenge, sending this moth to Pennsylvania. That's a joke. I don't think they did that on purpose. So this box tree moth is native to Asia. And it's first confirmed near Niagara Falls in New York State in 2021. And when I was developing these tools, in last year, September, it's confirmed in Erie County, Pennsylvania. That's a sad story. But it also gave me the potential to test my solution. So the box tree moth has 4 life stages. The main problem is the caterpillar consumes the boxwoods, that causing the defoliation that can potentially kill the trees. This map shows the box tree moth spread in Europe. In just 1 decade, we can see the spread. And one potential theory here is that we're preparing for the Olympics that help this spread. We don't want that to happen here in the US. So the current challenge, on the left side, the box tree moth has 2 color moths, the light moth and the dark moth. And both has this very similar other species to them. Even entomologists may need to take a closer look. For example, here, if I ask you, do you think they are the same species? I don't think we have, well, entomologists here.
I'm not this.
I'm not either. I'm a trained agent here.
But from color.
Yeah, so we can see that on the left side, there are these white dots on each wing. So this one is the invasive box tree moth. But the other one, the melon wall moth, we can find it very common in Pennsylvania. The current practice, we rely on the nursery experts to file the report. Then USDA, if we find it in one county, we will file the quarantine that you cannot ship your boxwoods outside of that county. Let's take this scenario. Imagine this is your beautiful boxwood garden. Do you want it to look like this or this? Well, now I tell you the problem is caused by this tiny moth, or specifically this caterpillar. But then today, you spot this moth in your garden. What would you do? File a report? Call your entomologist friend? Well, how could AI help? So here I developed this web portal that's called MothNet. Well, everyone can be the user here. Just by one simple click, then you just leave everything to AI. And then of course, we collect the data you uploaded to further improve our model. And I used this popular YOLO everyone's talking about. So the data set I got is from, it's called an iNaturalist, which is the data science tool that is very popular for entomologists. So I split the training, validation, testing for 70%, 20, and 10. And I try to ensure that I have the balanced objects for box tree moth and melon wall moth. And for box tree moth, I included both the dark and light moth. And we can see from when we annotated the image, we notice most of the images containing just one object, which means one moth in one image. Sometimes we have maybe 2 or more. So I tested out several different YOLO models, including version 5, 8, and 10, and 11, sorry. So for all of them, the result was pretty good. The M8050 exceeding 94%. For YOLO version 11, that we have the balanced precision and recall. So this attention map I extracted from the last layer, try to visualize which pixel is contributing more for this detection. Well, let's see how it works. So this is the portal. You can scan this QR code because I already deployed it to Penn State server. So after you upload, we will ask you to put the location. For example, Starkville, you found it here. I hope it's not going to spread here. Or you can directly acquire the GPS location. And we also, from the result, we tell you how confident we are about this detection. And use the confidence threshold we filled out. For example, if the confidence threshold is below 90%, we will not trust this result, and we'll tell you it's probably not a box tree moth. Now we can identify, but how do we monitor the population? The current practice is that we use this pheromone trap, that we put female pheromone to attract the male moth inside. it's a potential way to control the population as well. But the problem is we have to manually count how many moths there. Or if the trap is full, we have to clean up. Why don't we just add one sensor? So I tested several infrared sensors and I chose this photoelectric beam sensor. Each time when a moth goes inside, it will put one count. It's demo time. So I tested on the artificial boxer moth. Each time we drop the moth inside, the LED light flashes. That means one count. And this is a very easy way from just a serial communication. We can store these numbers to our SD card for further check or to the display. And compared to the commercial trap, this is the cost increased. Well, you may say, wait, Yanqiu, you have this vision model already. Why don't you just add a camera and you can detect and count? But if you have ever worked with the traps, or you can just simply search on the YouTube, you can see we have to wait, for example, like one night for all the moths to be dead. They are all flying around, very messy data there. Even though they still can stack on top of each other, and this is very challenging for AI models. Therefore, I come up with this design. So from the picture, this is the expected the moth path. From here, the entrance, the moth will go inside, and we have this killing mechanism that makes the moth drop to our platform. On the top, we have the camera. When the moth is detected, it will trigger the motor to rotate. So therefore, we clean the moth to our secondary container. Here's the outside view of the trap design, and then the inside view, the key feature is the moth sweep collector. And then for the prototype, I choose the 4K web camera, and for the self-cleanup mechanism, it's achieved by the stepper motor. This is the expected image that is collected. Let's see how it works. So when the moth is detected, it's swiped to our secondary container. Well, it's artificial. The moth is moving just because of the stepper motor is shaking. So then compared to the previous version, this is the cost increase. Well, I'm graduating, so I'm currently training the new students to work on expanding the data set, further improve the user interface, and also we will potentially deploy this trap over like Pennsylvania, but potentially working on same solution to very common moths there. And so I do see the potential of this solution to other species as well. Like we can expand the data set, make it like a universal tool, and we could also have this remote control of our traps so that you don't even need to go there. Well, with that, I would like to thank my advisor, my collaborators, and especially Penn State Extension to reach out to us about this problem. Well, my work on the moth maybe impressed the University of Tennessee people, so I got hired as an assistant professor to work on bigger animals. Well, so if your farm has a moth problem, I'm the person. Thank you. Yeah, that's my Penn State email. Welcome to Connect and scan the QR code. That's my LinkedIn. Thank you. Any questions?
Thank you for your nice presentation.
Thank you.
Yeah, and we are going to be neighbors
yes.
soon. So 100 mile away from Cookville to Knoxville.
Yeah.
Anyway, so we have 5 more minutes, so if you have any questions, please feel free. Okay, go ahead, sir.
First of all, apologies for coming in late for your talk. It seems like it's a very good one. And I really appreciate your commitment to prototyping and iterating on what you're doing.
Yeah.
And you want to continue doing this in leaf systems?
Yeah, we will. Yeah. Oh, you mean for the beef?
Continue the approach of prototyping?
Yes. Yes. So actually not for the beef, so I'm not there yet. I'm joining University of Tennessee from like June. But I'm working on the proposal with my colleagues there to try to have this kind of like smart nest for chicken.
Okay.
So that's like very similar, like smart trap to the smart nest. Yeah.
So did you integrate the LAR technology into like doing that? Because it's long range, you know, putting it into the IoT system.
Yeah. Okay. Thank you.
You explained about the modified design, right? For each trap, you have to keep a camera. So, like, if you have, like, if you take a hectare of the lot, so if you want to keep a trap around like 3 or 4 places, like based on the size, so it's too expensive to keep each camera, like, for each trap.
Yeah. That is actually the consideration. So USDA warned us. So they really care about the cost. That's why I'm like very transparent, put all the cost here. And what we're going to test is the beam sensor, just to achieve the counting first. But then, I mean, it's always good to explore more, to apply the vision model we have to have this customized design. And maybe I can apply it to Apples, and where they have more money.
So you told about the model and some software, like it is free for everyone, right?
Yes, yeah, you can directly scan this. Did you get that? You can scan the QR code and sign up, so you can use it.
Okay, is it applicable for any type of mods, like?
That's our eventual goal, but for this one currently, I just worked on like 1 year, and I just did this boxer mod and metaform mod. Great, thank you.
Any more question? Yes. You guys are working almost same.
Yeah, we talked before this.
Yeah, this is a very good innovation. I just wanted to apply to use the stopper motor somewhere with the clearance. So, and you are detecting them at night, right?
Detecting the mod,
At night.
Oh, and no. You mean during the trap? In the trap?
Yeah.
No, in the trap actually you can. It's not during the night.
Okay. So I just wanted to ask about the energy consumption of the motor. Like how many times does it rotate to clear the
insect?
The insects.
Yeah,
and
this is.
How is the energy consumption of the power source?
Yeah, we need to include those information like later after we deployed it actually in the field.
All right.
Yeah, that's a good point. Thank you.
Any more question? So would you mind to show, just describe a little bit about your stepper model, okay? So how you control that? Is automatically rotating, or as soon as it detects?
It's detected, then we will trigger. From the Arduino, we can understand the code.
So that triggering, automatic triggering, right?
Yeah, yes.
Okay. Good. Any other? Thank you for your nice presentation.
Yep, thank you.
And again, congratulations for both for your new position as well. Okay, so our next presenter is Udai Bhagia from Texas A&M University. Yes, go ahead.
Hello everyone, or howdy, as we say in Texas. I'm Uday. I'm a master's student in data science from Texas A&M University, and this work is part of my graduate assistant research work. And I was working for the past 1 year with a wonderful research group in Texas A&M. We have grad students, myself and Sejong Moon, Iklu and Adelu, and some of them are here. And we have wonderful faculty and advisors, Dr. Duffy, Dr. Tedeschi, and my advisors, Dr. Karun and Dr. Yalowdi. This is a photo of our group from last week. And I would like to thank Texas A&M Institute of Data Science, Texas A&M AgriLife Research, and Department of Animal Science from Texas A&M for supporting this research. And I would like to thank especially Dr. Cook for allowing us to take videos for his animals for one of his trials. So I'll be talking about making a computer vision system for detecting a common disease in beef cattle or other types of animals in livestock production. This is called BRD, it's bovine respiratory disease. And we will focus on how to make a computer vision system for this. And so BRD, it's also known as shipping fever. It's a common disease caused by virus, bacteria, or stress. And the name shipping fever comes from the cattle during the production stage. They travel from one facility, one producer to other producer, and during this shipping, they are in a restricted environment, and they get stressed a lot, due to which some of them will be getting this disease. And since this is contagious, it can spread to the other animals in the production, and it can be deadly, and it causes a lot of losses in livestock production. So it's important to detect this early so that we can prevent other cattle in the production system. And traditionally, this disease is diagnosed using a DART scoring system. DART stands for depression, appetite, respiration, and temperature. And how it happens is farmers go look at each like a group of cattle, and they manually score this DART scores visually, just looking at how the cattle are responding. And if we imagine a farmer dealing with like 10,000 cattle or 100,000 cattle, which is not exaggerating in US. So it is really hard to do this visually. So it's important to make automated systems using AI to detect this early. What can computer vision solve? Most of you may already know this, but I'll go through like few basic things computer vision can solve. We can, given a camera feed, we can detect objects that's drawing bounding boxes around them, or do a pixel level classification, which is called semantic segmentation. And when we combine both of this, we can actually get pixel level information of different objects of interest present in an image. And there are other types of computer vision algorithms, techniques like image classification, pose estimation, and we can combine different types of computer vision techniques to make a system that can detect this disease. So this is the design we thought of. So when we get a video footage, we can first locate the animals in there, then try to identify which animal is like which animal, like cow 1, cow 2, or their tag numbers, and then try to predict the activity, respiration, temperature, and over time combine these things we predicted into profiles, like an activity profile or temperature profile, and using this profile we wanted to predict the DART score. And in this presentation, I'll go through some of the modules we developed. This is an ongoing research. It's a more visual representation of the design we thought of. So the first module in our pipeline is instance segmentation. And for this, we are using a data set from a Calingate barn facility in Texas A&M. This facility has roughly 5 cattle in the pen. And when we get this data set, it consists of a lot of videos. And doing annotation for segmentation is quite labor intensive. So I thought of some smart way to do this. So we can use some foundation models to get the annotations and train smaller models to get the best performance out of them. So after trying SAM and other types of foundation models, I found a grounded SAM, which is a combination of grounding dyno and SAM from Autodistill to be most effective. And after auto-labeling around 800 images, I manually picked the good ones from them. it's really important to feed the models a good data set with the least number of false positives or least number of false negatives. So here is an example of the images that I picked and that I did not pick. If you look at the right side, on the top, one of the curve within the pen is not detected. Same case in the bottom right image. And after dividing it into training and validation and trained a YOLO V8 model on this, and we got a mean average precision from IOU 50 to 95 of around 90. This is a tricky task to do, to identify animals. And I have seen some of the presentations during the conference covering this as well. So using the segmentation model, we have 5 cattle in our videos. So we manually created a data set. We can do identification in a supervised way or unsupervised way. Both have their pros and cons, but we need to have a data set to validate our methods. So first we created a data set, and this data set, it covers different orientations of each cattle. And one of the interesting things here is the images have their backgrounds removed. I'll talk about it more when we come to activity, why we did that. First we tried unsupervised way. Our research group did some experiments on doing identity in an unsupervised way before, but we didn't try on full cattle images. And when we tried to use the same techniques on this data set, we were not really able to separate them. The reason can be because when we look at these images, each cattle has different orientations, and it's hard for a image feature extractor to maintain this separation, because it may categorize all the cattle from the front side into one category rather than different cattle into different categories. But since we have a classification data set, we trained a YOLO model anyway, and it gave almost 100% accuracy in distinguishing these. Our next task is activity recognition. Using the same segmentation model we have, we again generated an activity data set. We defined 6 different classes, and we looked at the videos and tried to observe what these cattle are doing. And we found cattle are mostly spending their time doing these kind of activities. Either they're lying down, or there is a water pump on the side of the pen. Are they drinking water? Are they feeding from the bung? And sometimes when they are feeding, their head is all over the place, so the feed falls on the ground. So we made another class saying, are they feeding from the ground, or are they standing still, or are they walking? And in the identity data set, we removed the background, but in activity, we kept the background, because when we are trying to predict identity, we only want to look at the cattle. But when we are trying to predict activity, we want to look at its environment, what is it doing, how is it interacting with the environment. And we trained a YOLO V11 on this, and we got good accuracy and FO score. We can see some examples of activity recognition because it's interesting. The positive samples are doing good with high confidence, but the more interesting things are negative samples, like why the prediction is that way. For example, in the first 2 images, the model is predicting these cows as walking. The reason is because if you look at the legs of the cows, it looks like they're kind of walking. And if you look at the third one, it's predicting as feeding from bunk, even though it's not eating. The reason is, when it's feeding, the head is closer to the feed bunk, and model tends to think that when a cattle head is close to a feed bunk, it is feeding. It's one of the reasons why it's predicted like that. And in the 4th image, it's actually standing, but it predicted as lying down because it cannot see the legs. Sometimes it happens. And the 4th the last image is also like that. So we have seen segmentation, identification, and activity recognition. And when we combine all these and apply these on every frame in the video, we get activity profiles. So what are activity profiles? These are like for each cattle. What is the cattle doing in a time window? So here I have for this, in this pen, I am showing the activity profiles for a time window of 20 minutes. So I don't have the video, but if you look at, when I observed, the cow one is always spending time at the water, like it's drinking water, and the cow 3 is mostly like feeding in the field one, even though nothing is there, I don't know what it's doing. And other cows are trying to, just standing, and the cow 2 tries to drink water, but the cow 1 kind of forces it away. So, and we can see that behavior in the activity profiles. For the cow 1, we see the blue bars, which means it's drinking water. And for the cow 3, we can see there is a lot of green, which means it's feeding from the bunk. And in the activity profiles, there are gray regions, which means when the camera is not able to detect that cow, when the cow is going away from the perspective of the camera, it's just not detecting that there is that cow in the frame. So our goal in this project is to make this model for real time, like real scenarios. So the previous data set, they are not close to a real scenario, but we have some feedlot facilities in Texas A&M, and we started collecting data there. We got the opportunity to record video footages on actual sick cattle, and we have the data for that. So we put cameras in 4 different feedlot pens. This is how a data acquisition setup looks like. We have 7 cameras covering 4 pens, each pen having 10 cattle, and we recorded for 7 weeks. And during the 7 weeks of time, we know like which cattle got sick on which day. So we can use that information as ground truth to test our models. Right now, so each pen has 2 types of cameras. One camera that looks into the feed bunk, and it has both optical and thermal cameras. We want to use thermal cameras for predicting temperature. We have different, another type of camera that is looking into the feedlot. So this predicts activities, focus on activities other than feeding. And we are trying to expand our segmentation, identification, and all of the activities and temperature respiration to this data set now. And one of the issues we were facing was using auto labels or transfer learning from our previous data sets to do segmentation on this. But when nothing works, we have to annotate. So we did annotation manually, and one of the reasons why it didn't work is there is a metal bar in between the cows, which is creating a separation, and the model is not trying, we are not able to predict that. And after doing annotation, we can see this clear separation, and all of these are prediction measures. And we also have IR footage. We wanted to utilize this to get the temperature profiles of cattle, but there is some mismatch between the sensors. IR sensor and visual sensors have different specifications, different resolutions, and different aspect ratio. And we tried to match this footage and use the predictions on optical camera to map on the IR footage. Now we're trying to...
I would like to stop it here. Sorry to bother you. Actually, it's 12 p.m., so everybody is ready for lunch. So I want to take a couple of questions, if you want, from what he presented so far. Go ahead, sir.
So I love the model which you have so far.
I saw.
Clinically, when you're out there, the first thing you'll see is nasal discharge. You don't have one of those as options. As a veterinarian, those are critical in diagnosing. We've seen this problem. We had our sensors in, and we picked it up real quick. Temperatures will take. So once 90 knows, if we didn't catch it that day, all of them would have been sick. We had to spend how much on Jackson?
Well,
Yeah, how much on Jackson. But great models, I think you should get some of your vets in, and make sure the clinical science matching up with the diseases, you know, so. And
And it seems like with early pictures, all Hereford-based cattle, when you're picking out animals, do you more film color gradation? Because if you get all black cattle, that's going to be a lot tougher.
We have those in the field artists. And right now we are conducting like experiments on differentiating between them.
Yeah. So thanks for like sharing all the challenges you had. Like yesterday I had discussion with the Mavis here at Mississippi. So we were talking about like the behavior, because from your image, the walking and standing is really hard to differentiate, right? But then probably can do like a pinpoint detection that can, you know, and I would explore that.
We have plans of using video information. Right now we are doing only predictions on images, but if we do pose estimation with key points and then look at in a timing of 5 seconds, then we may be able to get better predictions, but that needs a lot of ground truth. So we are in the process of making that ground truth.
Okay, great. Thank you.
Yes, sir.
Just final quick, in your training data set where the water tank was in one corner of the image, is the model just going to say any animal in that corner of an image is drinking, or do you have a variation in your data set about where the tank is relative to the camera?
So in this data set, we only have cameras at one point, and that bias can happen, like model predicting with water as drinking water all the time. But sometimes when the cow is not drinking water, it is predicting as just standing, even though there is a water pit.
proximity sensor.
We have those samples in the data set.
Yes. Yeah. Okay. Thank you.
Yes.
I think I'm going to ask you to skip to the end. Has your model been able to predict disease at the same accuracy or efficiently compared to a veterinarian?
So we have the disease data, which cattle got positive VRD. Right now we are yet to develop the final modules in our pipeline. So we still don't have the answer for that, but we are hoping, we are thinking that we can do a good job in predicting that.
Yeah, just a quick, I am not an animal scientist guy, okay? Can we reduce, mark some of the activity when the cows are inside of the barn or in the pen? Can we reduce some of the activity or mark some of the activity so that your model performance can get better?
Yeah.
When they're in the barn, I'm not talking about when they're grazing or something.
So merging activity, like we can see some patterns, like for example, when a cattle is lying down, before lying down and after lying down, it has to stand up.
Yeah.
And it takes some time for it to lie down. It takes for some. We can use this common knowledge to improve the activities, definitely.
Thank you so much. I'm sorry. Thank you for your attendance.
What kind of cameras are you using? Because they seem very clear.
Good job.
I really like most of the presentations. Can you sit there? Yes. We are excused by the security and
Okay. So it's security camera.
Yeah, okay. Yeah,
I think it's.
Yeah, I connected.
Yeah.
Okay, sounds good.
Your annotated images are very cute.
Okay, my question to you